smoke alarm circuit. Probably the worst possible smoke alarm circuit in the world, but a smoke alarm circuit nevertheless. Appeared first, I think, where I've come across it, electroschematics, and was then picked up by Talking Electronics, who put it into a spot mistakes section. And yet the biggest mistake to me just happened to be this FET transistor, this BS170, connected through its gate down to this capacitor, a 4.7 microfarad capacitor. FETs, I can't say I like FETs. I've had a lot of problems with them. And when I come across this, I thought, no, alarm bells rang 1,000 times. That's not right. If that capacitor charges up, of which there must be some dispute, as said down here by the people on their comments, this is a state-controlled rectifier, a thyristor, a latch. The whole point is, once switched on, it stays on. But to stay on, it needs a current flowing through it. If we look at the data sheet for it, and that one happens to be a BT169, then here we have BT169, and if we look at its parameters, the gate current is about 200 microamps. The latching current is a maximum of 6 milliamps, and the holding current is 5 milliamps. So to hold on, it must have, from anode to cathode, 5 milliamps to guarantee it. That's the maximum. While I'm on it, I might as well look at the thyristor, or thyristor, yeah, state control rectifier I'm going to use, which happens to be a 2N5060. If we look at it, it has a gate trigger current, 200 microamps, same as the other one. A holding current of 5 milliamps, which is same as the other one. The switch on current, I don't know what that is, but basically it needs a trigger current of 200 microamps and a 5 milliamp maximum holding current. So both have the same. And both need 5 milliamps coming down here. Well, nothing's going to flow into the gate of the FET, and certainly once the capacitor is charged, nothing's going to flow through there. So this is redundant. We don't need it. Or at least we could put a simple transistor in there, NPN transistor. So let's have a look at the circuit then. If I have a look at the circuit, what I've done is to build it onto a piece of board which has lots of holes in it, and we push pegs through the holes and then solder onto the pegs. Very old technology, reminiscent of the old breadboard, what was actually a breadboard, a wooden breadboard, and one knocked nails into it and then soldered onto the nails. So this is an updated version of that. This is actually some student's project from the past, although I can't actually read the name that's on it. Anyway, I've stripped it down so I can use it again. Maybe, maybe not. But this is what I've done. This particular one, I've stuck paper over the top so that I can draw the circuit on. That to me is the advantage over a breadboard. If I had a breadboard, yes, I'd have my LED, yes, I'd have my resistor, yes, I'd have my FET down here. but I wouldn't be able to see the picture underneath. What I've also done is put my 4.7 microfarad capacitor in. Over here then I've got my FET. I've put in here a circuit ready for reuse or use later, which wires onto this, and I can use that instead of the FET. So that is an LED 1.2 capacitor resistor, and then down here just a simple PNP transistor, because it seems to me that this has been a modified circuit, sort of thing a 16-year-old would do to pass their exam, to find a circuit which originally had an NPN transistor here, so that the gate current would be greater than the 5 milliamps needed to hold the thyristor on, and that's what would have been here. To modify the circuit then, they've put in a FET. It doesn't really seem to make sense. But let's try it. Let's see what we got. So here's the circuit. I've got a multimeter here that's going to tell me the current into the circuit. So let's put that on to 200 milliamps. And we can't see it, can we? Well, I can't. Let's see if we can adjust easily to see it. If we go up and down, is that visible then now? Everything visible there. Let's tighten up and see. What we can see. So no, I still don't think I can see that. Let's turn that off. There we are. Yes, now we can see 12.3 milliamps coming into the circuit. Been a bit naughty and put an LED on so I can tell if the power on the circuit is on. So of that 12 milliamps, then about 1 milliamp is going through my part of the light slotted opto switch. Slotted opto switch, worst possible thing in my opinion for a smoke detector, but here we have a slotted opto switch. This one happens to be dead. I've killed it somehow. It's a second-hand jobber. Essentially all you have is a LED transmitter and a transistor receiver. This particular one's got 3 legs, so one's got to assume it's a Darlington transistor, which makes it a lot more sensitive. And all they do is slot into there, and then there's a slot down each side of the, I don't know if we can see that or not, down here's a slot, down there's a slot, and that means that the LED can shine onto the transistor and drag it down low. So that's a slotted opto switch, which I've got over here. So that I can just put something in between it. If I then find something to put in between it, a piece of clear plastic, difficult to see. Why use clear plastic? Well, the point of that is that a guy has looked at this original circuit, Jim Keith, and has looked at the opto, slotted opto switch, and put his soldering iron underneath and put some cord solder on his soldering iron, and found that the smoke from the soldering iron went up on the slotted opto and gave him quite a large amount of change in the slotted opto. He then did the same thing with transparent polyfilm, found that also gave him an effect, but not as much as the smoke. So he started experimenting with polyfilm, much easier than smoke. The interesting thing here is, I don't know whether the smoke lingered here, but when I tried it, the whole of the slotted opto heated up with the heat from the soldering iron just underneath it, and I found that it took a while for it to actually come back down to the 4.2 volts that were on it before. So I suspect this is heat from the soldering iron. But nonetheless, we don't get that with a transparent film, so let's try it with transparent film. So here we have a slotted opto, here's transparent film, and we can put it in and it doesn't work. So what we need to do is to look at the output from the slotted opto switch. If I connect on there and look at the voltage, I seem to get 0 volts. Why is it 0? Seem to not have a good contact. Let's try there. No. Try there. And I find I've got 0.71. I need to alter this to get, shucks. Put my hand over the opto switch and I can see that the voltage rockets up. In other words, the opto switch is getting light into it from somewhere. Looks like it's coming in through the window. So can I move the slotted opto switch so that it's not getting the light? Difficult. And can I alter my variable resistor? Well, I can't get to that without altering it. Let's try a block. See if we can block the light. Right, there we've blocked the light. Let's try again with our slotted opto with our bit of plastic. And here, presto, our LEDs come on. So it's worked with a bit of clear plastic film. Difficult to see on the... But according to Mr. Keith, that is as good as smoke. Although, if this was in a room and it needed the amount of smoke from a soldering iron resin, then I would think one would be choking first. Right then, so our LEDs come on. So what do we want to show? Well, we want to show that this isn't, in fact, let's remove this, don't need that for a moment. Let's show that that isn't due to this thyristor coming on. The easiest way to do that is to disconnect it from the thyristor. So now we have no connection between this FET and this. Which thyristor there? Up there's the thyristor, can't see that. Up there's the thyristor, no connection now to the FET. The connection is, all the LED is held on by, is this capacitor which is charged up. Does that matter? It's worked. Well, yes it does, because if I disconnect the power and reconnect the power, I can't reset it, because this capacitor is charged and will continue to be charged until it runs itself down. It self-discharges. Can I prove that? Well, let's try that with this voltmeter. Well, why bother? Try this voltmeter. Find my lead and connect that onto the capacitor. Once it's on the capacitor, it very quickly discharges the capacitor and the LED goes out. So to discharge this circuit, we actually need to short out the capacitor, and on the circuit as drawn, it just ain't gonna happen. So, as I suspected, I think this circuit's been fiddled with and somebody's tried to modify it. Let's take the output of our SCR, state controlled rectifier, and put that into a transistor. Let's block my light again so that hopefully, if I can find it, I can put this on, and oh yes, it's come on just due to the clear film, and we can see that the thyristor has latched on, because if I now remove the connection, the thyristor goes off and the LED goes off. I can do the same thing, bring it on. I don't know if that's visible, is it? I've just brought it on using the film, and now if I short out, being very careful, how can I short it out? Let's short out that thyristor and short it out, because one way to switch it off is to short it out. Oops. And there we are, just shorting out the legs of the SCR has switched the transistor off, proving it was the SCR that was controlling it. So my belief is that this FET is an afterthought. Down here, the FET down here is an afterthought, and that originally it had a transistor in here. A fascinating circuit, and I've a lot more work to do on it. But I think that more or less confirms to me anyway that the circuit's been modified by somebody who didn't really know what they were doing. The interesting thing is, if I replace this, where does it go? Replace the transistor and put the FET back in, and replace the capacitor with a resistor, if I can get it into the sockets. Maybe I need to give up on this. Or use some pliers. Put that into there. Bumbly 1 and Bumbly 2. Ah, there we are. Right, so now I've replaced the capacitor with a resistor. So let's see if now, when I use my clear film, the LED comes on, switched on by the state controlled rectifier. But if I disconnect my connection to the state control rectifier, it goes off. If I reconnect it, it stays off. So why have they put the capacitor in there when all it needed was a resistor? Just can't understand it. Don't make any sense to me. There it is again. I don't know if you saw me switch it on. And there it is, and I could of course short out my state control rectifier again, but that is a bit too complicated. So there's the circuit working, but in no way, manner, shape or form should a circuit like this be used as an actual application. I'll go into that on my next video on this circuit, which I've really enjoyed playing with.